bulk modulus, specific heat, and thermal coefficient of volume expansion of a gas derived from thermodynamic equations. Good morning. In our textbook, we have several tables of values relating to solids and liquids, and some of them have gases as well. I want to show you how the values in the tables for the gases can almost be derived from the thermodynamic equations PV equals nRT. Of course, I always think of something more to do while making a video. Let's start with density instead. So instead of calculating 3 quantities, I'll be doing 4 quantities. We have in this table 4 quantities giving densities of gases at standard temperature and pressure. Let's choose oxygen and begin by taking the ideal gas law and find out how many moles of oxygen would be in the air in a pure oxygen at standard temperature and pressure. PV equals nRT, and I want in 1 cubic meter of pure oxygen at standard temperature and pressure because it's given in kilograms per meter cubed. So our pressure at standard temperature and pressure is 103,100 pascals. Our volume of 1 cubic meter of pure oxygen is 1 meter cubed. We have N, which we want to solve for. R is 8.31 joules per mole Kelvin. And our standard temperature, it says, is 273 Kelvin right there. So plugging that into the calculator, I have 45.445 moles. So looking at oxygen on our periodic table of elements, we see that it has a molecular mass of 15.999 moles or grams per mole. So oxygen has an atomic mass of 15.99 grams per atom, but O2 has twice that mass. So if you take the 45.45 moles of molecular oxygen times 2 atoms per molecule, we'll have 90.89 moles of oxygen atoms. Then, multiplying by 15.999 grams per mole, we have the mass of a cubic meter of oxygen atoms at STP, standard temperature and pressure, at 1454 grams. But our table gave the mass in kilograms per cubic meter, so I divide by 1,000 to get 1.45 kilograms per cubic meter. So, how did we do? We got 1.45 kilograms per cubic meter with our calculation, and the table has 1.43 kilograms per cubic meter. What accounts for the discrepancy? Probably the fact that oxygen is not an ideal gas. If we took into account the effective size of the oxygen molecule and the interatomic forces between oxygen molecules, these are two features of non-ideal gases, we might get a better match. If you're curious about those things, you can look up van der Waals equation, but I think this is a very close match. Next, let's see if we can find out the specific heat of steam. The specific heat of steam is shown in table 11.1. It is the only example of a gas in the entire list. First, let's compare the relevant equation for specific heat to the ideal gas law. Now, it's not immediately obvious how to apply the ideal gas law to this. Okay, the main thing is we're not going to be using PV equals nRT, but rather Q equals NC sub P delta T. How can I explain why we'll be using Q equals NC sub P delta T? How can I explain why? Since I don't feel I can explain it well, I'll try to explain it at least poorly. What we're going to be dealing with is an isobaric process, which we can look up in table 12.2. In an isobaric process, the sign convention used in Table 12.2 is not the natural sign convention. The natural sign convention would be if you add heat to the system, that heat does some work on the environment by making the volume increase, and it also increases the internal energy of the gas. Then we could make these replacements that Q is nc sub p delta T. The work done on the environment is opposite of the work done on the gas. It would be nR delta T, which would also be pressure times the change in volume. And then the delta U, which is the change in the internal energy of the gas, is always the same thing, nc sub v delta T on every one of these. So delta U is nc sub v delta T. And so then replacing Q with this, you get nc sub p delta T equals the work done on the environment plus the change in internal energy. The reason I like this a little bit better is it can be factored out to make this relationship between the specific heat at constant pressure and the specific heat at constant volume plus the ideal gas constant clear. So the reason that we're going to be using C sub P as the specific heat at constant pressure instead of R is because we want the heat exchanged instead of the work. Why do I say that's a poor answer? Because it's mathy rather than conceptual. I've essentially just told you use C sub P instead of R. I've told you there's a distinction, but I don't think I've explained exactly why the distinction exists. That is in large part because I currently have no explanation I feel entirely satisfied with. Is it because the heat increases the entropy of the gas, and some of that entropy goes towards doing work, and some goes towards changing the internal energy of the gas? Is it because delta U is equal to Q plus the work on the gas? Yes, I think it can be derived from that, but it still feels mathy and unsatisfactory. So I've become sidetracked, but I think that in order to resolve this issue for now, I'm going to make a statement that will actually make it more mathy, yet strangely at the moment make me feel better. It isn't really whether or not an explanation is mathy that makes it feel non-intuitive. It's a failure of definitions. A good definition has at least two representations. In math, this can be accomplished by stringing together a lot of equal signs. All of the values on the right can be derived from the triple inequality on the left. For instance, P delta V equals nR delta T. That is right there. P delta V equals nR delta T. You can also say delta U equals nC sub V delta T. That is right there. Delta U equals nC sub V delta T. And Q equals nC sub P delta T, which is right there. nC sub, or Q equals nC sub P delta T. So thing we got rid of was the work on the environment. So this no longer has that sign ambiguity because work on the environment was negative of the work on the gas. Okay, before I got sidetracked, here was what I was planning to do. I wanted to show that the specific heat per mole of H2O, the specific heat per mole of H2O, 35.4, and the specific heat per mass of steam, 2010, was the same. So looking at these two equations, Q equals mc delta T and Q equals n C sub P delta T, if the mass of a mole times 35 times, if the mass of a mole times 2010 joules per Kelvin, joules per mole Kelvin, is pretty close to joules per kilogram Kelvin, is pretty close to 35.4 joules per Kelvin. It is, they are pretty close. They are pretty close to the same value. So in H2O, we've got 2 hydrogen at a mass of 1.008 grams per mole each, and 1 oxygen at a mass of 15.999 grams per mole. So the total mass of a mole of pure water vapor is 18.015 grams, or 0.018 kilograms, per mole. So multiplying that value by 2010 joules per mole Kelvin, we get 36.21 joules per mole per degree Celsius. That's a pretty close match to the 35.4 joules per Kelvin given in table 12.1 for water. When doing the density calculation, we accounted for the discrepancy between the actual density of oxygen gas and the value predicted by experiment by recognizing that van der Waals forces kept oxygen from being an ideal gas. I'm thinking we could do that again, except for a little problem. The two values we used were 2010 joules per kilogram per Kelvin and 35.4 joules per mole per Kelvin were both experimental. So now this discrepancy is probably due to the fact that I assumed the 2010 was based on the ideal gas density of steam. In fact, because of interatomic forces between the molecules, the density of the steam would be a little bit higher, and that is reflected in the higher specific heat listed here. Okay, now let's look at the thermal coefficient of volume expansion. You'll see here there is a footnote regarding air at 0 degrees Celsius. Gases do not have a specific value for volume expansion coefficient because the amount of expansion depends on the type of process through which the gas is taken. The values given here assume the gas undergoes an expansion at constant pressure. So let's see if we can derive this value for the thermal coefficient of volume expansion using PV equals nRT. And our equation beta, our thermal coefficient of volume expansion, is that the change in volume divided by the volume is equal to the thermal coefficient of volume expansion times the change in temperature. Now we saw earlier when we changed the temperature, it affected P delta V over R. In an isobaric process, we basically can maintain this relationship N delta T equals P delta V over R. So that's not a general, that's not true in general, but just true in the case where we have isobaric processes. So now we're aimed toward getting beta equals delta V over delta T, beta equals delta V over V delta T. So we want to try to manipulate this thing algebraically until we have something like that. This comes from the ideal gas law. We can get the delta V over delta T out by multiplying both sides by R over P times R over P delta T. And then divide both sides by the volume, and we'll have NR over PV. And NR over PV turns out to be, because PV equals nRT, it's just 1 over the temperature. So that's kind of cool, because that's what our beta is. It's going to be nR over PV equals delta V over V delta T. Turns out nR over PV is 1 over T, and our temperature here, they said, was 0 degrees Celsius. So 1 over 273 is 0.003663037, which is pretty close to 3.67 times 10 to the negative third. Now, assuming an isobaric process, then there is no dependence on what kind of gas you're using. So this is a little bit smaller number, so maybe they're using a little bit higher temperature. Actually, it would take a little bit lower temperature, 272.85 degrees, to get 3.665 times 10 to the negative third thermal coefficient of volume expansion. Okay, I have one more property that I'd like to confirm, property, before I end the video. We've got density, specific heat, thermal coefficient of volume expansion, but now I'd like to do the bulk modulus given in table 9.2. Unfortunately, there are no gases listed in the table, so we're going to have to look it up on the internets. As it happens, Wikipedia has not one, but two bulk moduli listed for air. The first is an adiabatic bulk modulus, and the second is an isothermal bulk modulus. So here's how you derive these two things. Notice that in an isothermal process, the energy exchange maintains thermal equilibrium, and the pressure-volume relationship ends up being pressure times volume is constant, because nRT is constant and the temperature doesn't change. On the other hand, in the adiabatic process, there's an equation that goes PV to the gamma equals constant, and gamma is this specific heat at constant pressure divided by the specific heat at constant volume, which turns out to be 7/5 for a diatomic molecule, which is mostly what the air is composed of, and so 7/5 is 1.4. You'll notice that that kind of matches up right here with the 1.42 times 10 to the 5th versus 1.01 times 10 to the 5th. All right. So anyway, if you basically you say the pressure is equal to some constant divided by V to the gamma, or the pressure is equal to K times V to the negative gamma, and take the differentiation of that, dP over dV, and then multiply that by V to get the bulk modulus, which is pressure equals B delta V over V, so B is equal to, as a matter of fact, let's edit that and say delta B delta P is equal to B delta V over V. And so I'm just plugging that in right here. The bulk modulus is negative V dP over dV. That's the same thing I do over here. And then I get, when I do the differentiation, it comes out to V to the negative gamma. Or rather, when I do the differentiation, the negative gamma pops out, and then you subtract 1 from the exponent, and then when you come down here, it's k gamma v to the negative gamma because we multiplied by v, so that minus 1 goes to 1, or goes to 0. Then when we multiply v to the negative gamma times v to the gamma, we end up, those cancel out, and we've just got the bulk modulus is gamma times p. So the bulk modulus of a gas during an isothermal process is just equal to the pressure of the gas, while the bulk modulus of a gas during an adiabatic process is equal to the adiabatic index of the gas times the pressure. So in summary, here's the entire rundown. We've got solid and liquid representations where density is rho equals mass divided by volume, and the ideal gas representation, which is rho equals the number of moles times the mass per mole divided by the volume. Specific heat, Q is equal to m times the specific heat times delta T. With the ideal gas, Q is equal to N times the specific heat at constant pressure times delta T. For the thermal coefficient of volume expansion, we have beta equals delta V over delta T times V in both cases, but it came out to turn out that that came out to be nR over PV, which was equal to 1 over the temperature for an ideal gas. And finally, with the bulk modulus, we had two different representations of this formula depending on whether you had an isothermal bulk modulus or a gas compressing isothermally or adiabatically. Thank you for watching. I know I will find this helpful to watch later. I hope you will too.